Hi, welcome to this video that shows how to map EtherCAT PDO messages to pass an encoder position from a Control Techniques drive to a TwinCAT PLC NC encoder axis. The NC encoder axis may be used as a master axis reference for function blocks like MC gear in, MC cam in, or a Control Techniques MC CT EGB axis function block. So the hardware that we're going to be working with in this video is a laptop that's been preloaded with the TwinCAT software. We've got an Ethernet connection from the laptop through to the hardware that we're using. In this case it's an IPC, but the steps are the same if it's a PLC or controller. We've got one port on the device that's configured for EtherCAT connectivity, and that's then connected through to an SI EtherCAT, which is an EtherCAT interface option that can be plugged into a UniDrive M700, which is this drive. Now, if you've got a dedicated servo product, so that's Digitax HD, in particular the M753 model, you'll find that the steps in this video are identical for that particular model of drive as well. Now, for the purposes of the demonstration, there are two encoders plugged in, so there's one attached to the application motor, and then there's a second encoder here. So the drive motor encoder is connected to P1, but the second encoder, so this might be the equivalent of a line encoder, that's connected to P2. And this particular device in our case is a 1024 PPR incremental encoder. So when you're dealing with PDO mapping or SDO mapping, the format that you specify the data that you would like to get has to be in the format of a CAN object, and then CAN objects have an index value and a sub-index value. Okay, but drive parameters, when you're trying to get hold of information like position, are in the format menu and parameter. Okay, so here's an example. We've got menu 20 and then parameter 21. We've got to do a little bit of conversion to make it so that it's in the format index and sub-index. So the beginning portion is fixed. It doesn't matter which drive parameter that's in the format of menu and parameter you're going for. It's always the same, so they all start OX20. And the last part, we have to convert the menu number to a hex value. So what you'll find is that decimal 20 converts to 14 in hex. Then the sub-index, it's much more convenient just to pass the decimal value through, because the PDO mapping interface allows you to actually enter hexadecimal or decimal values. So you might as well just use the feature of being able to enter in a decimal in this case. So in terms of conversion, if you're having any problems sort of making the conversion between decimal values and the hex equivalent, you can use the calculator in Windows in programmer mode. Enter the decimal value, it will be in decimal control by default when you first open it, and then the hex value will be there for you to be able to use. But to save you some time, this table, if you were to pause the video, you'd be able to read out the information that you need. So depending on which interface you've actually gone and wired your encoder to, you can read through this table and be able to get hold of the information that you need. So in our case, we're interested in drive P2, so I'm going to be using the index OX2003, and sub-index, I'm actually going to enter the number 158 because its parameter 158 is the location of the position information I need. And you'll notice that all of them, the data type is DINT. That's essentially everything that you need to be able to do the mapping. So lastly, slot 3, if you've got our dedicated servo product, Digitax HD, this last section isn't for you. Essentially, the slot 3 can't be used for position interfaces on that product because slot 3 is a kind of internal slot that's used for factory fit options. So in our case, if you were using something like a Digitax HD M753, that would contain the EtherCAT interface. So before we go too much further into the demo, I just want to point out that all of the steps, all of the information that you're going to see in this video is actually covered by a written getting started guide. So I'll just show you very briefly, and this guide is linked in the description, so if you prefer to learn from a book rather than a video, stop the video, go to the description, follow the link, you can get this guide. I'll just show you very briefly. So how-to guides, how to configure PDO mappings, and then under there, how to map a drive encoder to an NC encoder axis. So this section of the book follows exactly the steps that we're going to follow in this video. So first things first, so I've got a copy of Connect open, which is our drive configuration software. Again, there'll be a link to be able to get hold of this in the description. And what we need to do off the bat is we need to go and configure our P2 encoder face. So my encoder is already wired into the P2 interface terminal, so that's terminal 7 to 12 on the encoder D type. And now we're just going to go and configure that encoder. So I'm going to select parameters, menu 3, and then I'm going to be looking for the P2 interface setup. So what I'm interested in is I need to go and select the correct encoder type, which for me is AB. It's a AB, incremental encoder, and I need to set the number of pulses per rev to the correct number for this particular encoder, which is 1024. There we go. So that's essentially as much as we need. I'm just going to go and save that in the drive. There we go. And then we can go and have a look at our position information. So if I highlight this, there's our position information, and you can see I'm moving the encoder backwards and forwards, and you can see that the position is going up and down with me. So we can see that that is in fact working. So I'll leave it there. Right, next thing, we need to move over into the TwinCAT world. And what we're going to do first is set up the mappings to the parameter. So what I'm going to do is I'm going to double click on the drive, select the process data tab, and what you can see here is I've clicked on index 1A02. So this is the incoming mappings for PDOs, and I'm going to left click to highlight, then right click and go add new item to this set of PDOs. So I'm going to call this line encoder. So this is where our position information is going to come into. So line encoder, and then our index, which I'm going to enter in as a hex value 203. And then our parameter, because it's more convenient to enter it this way, is 158. That's all the information straight from the table. The data type is correct. You mustn't forget this, because if you get the data type wrong, the link won't establish properly and it's a DINT. Okay, so a 32-bit signed value. I'm going to click OK on that. Click yes to the following message, and then we'll have a look. So what you can see now is that we've got this new PDO mapping, but it isn't actually linked to anything. So what we've got to do now is create a place for it to be linked to in our system. Okay, so this is a really basic project. There's no software in it at all at the moment. All that's happened is we've told the programming environment this is the IPC that we're using, so it knows what hardware it's got. We've right-clicked on devices, we've scanned the network, we've found the EtherCAT interface, then we've told it to scan for boxes, and we've found the drive. Okay, beyond that, nothing else has kind of been done. Okay, so when we scan for boxes, an axis was added in for that, so that's a normal motion axis. But what we're trying to do is make it so that we've got an encoder axis, so that we can use it to input our encoder position. So there's no motion side to it, but you can have just an encoder axis on its own and use it as a master. So that's what we're going to do. So I'm going to right click on axis and go add new item, axis 2, you can just select OK to that. And then I'm going to set it up so that it's correct for the type of device that we're actually going to connect. So at the moment, so I've double clicked on encoder, I've opened up its properties, and then by default it comes up with this encoder type, which is simulated encoder. So if you're pulling in a 32-bit encoder reference, you won't actually get any position information available in the NC axis from that, so you have to select this one, which is encoder universal. Okay, so next thing that you might want to do is set up your scaling. So you have to set up these units so they match the unit scaling for the any slave axes that are going to attempt to follow this. So I'm just going to enter a number of 1,000 units, and I'm going to say that the number of encoder counts per rev are 65536. And the reason it's 65536 and not 4096 or 1024 is that any encoder that is less than 16 bits is scaled up by the drive to be 16-bit value. So even though it's only 1024 PPR encoder with quadrature, that'll be 4096 PPR, actually the drive scales it up to be a 16-bit encoder. Now that doesn't mean that you've got any extra resolution. It's not like a magic wand thing that suddenly gives you loads of extra resolution. It's not that. It's just all of those low resolution encoders, to make it convenient for them to work together, have all been selected to be scaled up to 16-bit minimum to match the minimum general resolution used by motion systems. So there we go. Also, it's worth pointing out that if your encoder is particularly low resolution, or you're getting a lot of mechanical resonance, something like that you want to filter out, here are your filter controls. You can engage this filter. So at the moment we've got a filter time for the actual position, so that's the thing that our slave axis, so our gear in type axis or EGB type axis will follow. You can enter some numbers in here and have that position value filtered, and it's a pretty good filter, to be fair. So next thing that we need to do, we need to go into our library. So at the moment you'll see that we haven't actually got any PLC open type function blocks, so our NC axis library isn't in there, so we're going to have to go and set that up. So I'm just going to do that now. So add library, motion, point to point, and we just need these function blocks. So I'm just going to go and do that now. Add library, motion, point to point, C. But I'm not going to add the homing one because for what we're doing we don't actually need that one. There we go, that should be enough. So now I'm going to come to our main program, again blank program, and we need to add in an axis ref. Okay, so axis ref is the basic construct for an axis in the PLC open specification. It's what the NC motion in TwinCAT is based upon. So let's take a look at that. So I'm going to say axis 2, and it will be of type axis ref, and there we go. So now I'm just going to build. The reason I'm building now, so if I go build solution, there we go, click OK, click OK, good. Okay, so the reason I built then is so that this axis will appear in the list of pickable axes when I try to link to my PLC here. So I've double clicked on axis, I'm on the settings tab, I want to link to PLC, and now you can see that axis 2 is selectable. If you haven't compiled, or you haven't successfully compiled, so if you've got an error and you compile, it still won't appear in this list and be selectable. So I'm going to click OK to that, and now we've got a place for our encoder data here to be mapped to. So let's go take a look at that. So I'm going to double click on line encoder down here, and here we have axis 2. Here is the encoder port, and interestingly it's already highlighted, so I'm going to click on that one and go OK. So what we can see now is that our PDO data now is linked through to a place that can absorb it, which in this case is the encoder input for that axis. So what I'm going to do is I'm going to activate the configuration to get that to go into the product. Click OK, and wait for the system to restart. Okay, so I'm just going to bring up, there we go. So if I bring that up to there, then I'll minimize it so that you can kind of see them at the same time as each other, hopefully. Gonna work? Possibly not. Let's take it over that way. No, I'm not going to be able to fit them on the screen at the same time, but basically if you see me moving this encoder reference, you see there the number changing, you can see exactly the same number there in the encoder interface. Okay, so that's the data coming into the link. Now the last thing that you're going to want to see is how that appears from the perspective of the axis. So you can see that we've got, I think it's outputs to PLC, and you've got active pos. So if I cancel that, what you can see is now, as I'm moving the encoder, actual pos, which comes from the NC encoder axis, well, so this is after all of the scaling. As I'm moving the encoder, you can see that encoder position is coming through, and that shows that if you had something to absorb that encoder reference, like MC gear in, MC cam in, or our EGB interface, that would be enough to drive it and to give it a position reference. Okay, hope you found this useful. Thanks for watching.